Good afternoon, grade 11 students. Welcome to our telematics session this afternoon, where we will be looking at synoptic weather maps. My name is Regan Ford, Geography Subject Advisor in Metro Central Education District. So, these are the topics that we will be covering this afternoon. Firstly, we will be looking at what is a synoptic weather map. We will then investigate weather station models. Your teacher would have done that with you already. We will look at the characteristics of synoptic weather maps. We will identify the differences between summer and winter synoptic weather maps. And we will look at the application of synoptic weather maps, how we can use it practically and how we can be tested on it in the exam. So let's get started. What is a synoptic weather map? On the sketch in front of you, the little map in front of you, you see an example of a synoptic weather map. Your teacher in class would have shown you, introduced you to synoptic weather maps, shown you what they look like, and I'm sure you've worked with them. But what is the definition of a synoptic weather map? So, the word synoptic very simply means a summary of the current situation, right? In any topic. Synoptic means a summary of the current situation. So in terms of the weather, what are the weather elements that we study? We look at pressure patterns. Atmospheric pressure, is the pressure high or is the pressure low? We look at fronts, cold fronts, warm fronts. We look at wind direction, is the wind coming from the northwest, is it coming from the southeast, etc. And the velocity or speed of the wind, at how many knots or kilometers per hour is that wind blowing? And then how will these weather conditions change or evolve over the coming few days? And that is the summary of the definition of a synoptic weather map. So we see that it sounds a little bit complicated, but hopefully by the end of the session you will have a clearer idea of what a synoptic weather map is. To sum it up in one sentence, a synoptic weather map shows the weather conditions at a particular time with different conditions and features with special synoptic chart symbols, and we'll be looking at those symbols also. Right, so let's start with the weather station models. Now, you would have been introduced to weather station models in grade 10 already, very basically, and in grade 11 now you will be, excuse me, looking at them a little bit more in detail. So what is a synoptic weather station model? And in front of you, you actually see an example of one. So, a synoptic weather station symbol is a little diagram, a little symbol that shows us the weather elements that are indicated on the screen in front of you. So in other words, we can deduce from this symbol, we can see what the wind speed, the wind direction, the dew point temperature, the amount of cloud cover, the air temperature, and the precipitation was at a particular weather station. So if we're using South Africa as our base, across South Africa there are hundreds of weather stations who are measuring the elements of the weather on a continual basis. And twice a day, the South African Weather Services publishes a synoptic weather chart showing the weather conditions at the major weather stations in our country. And you can imagine if we have hundreds of weather stations and there's so much information coming from each weather station, it's going to take up quite a bit of space on the map to write all those things down. So what do? We summarize the information found at every particular weather station into a universally accepted symbol. This symbol, someone from the USA, someone from China, someone from a country in Europe or in South America will be able to tell the weather conditions by simply looking at the symbol, because the symbol is universal. It is used throughout the world. So let's have a look at the weather station symbol now, won't we? Right. So the weather station symbol is a way to show a lot of information about the weather without writing it all out, right? Just summarizing it, putting it in the form of a symbol. Now, here is the station model and key. Now it looks quite complicated. But it is not. So in fact, why don't I draw one for you, and then you can see what I'm drawing, and then we'll come back to this slide that you see in front of you, and I think it will make things a little bit easier. So have a look at what I'm drawing. So our weather station always starts with a circle. And that circle indicates to us the cloud cover. This circle is going to tell us more about the cloud cover. If the circle, I'm not going to color the entire thing in, but if the entire thing is colored in, then it means that the cloud cover is what we call overcast, right? We use varieties of 8, so it could be 1/8, 2/8, 3/8, the percentage of clouds that is actually visible in the sky. So here, the meteorologist will be looking at the sky, they'll be looking at a certain section of the sky, and they'll be saying what percentage is covered in cloud, okay? And that would be our cloud cover. So for example, if a quarter or 2/8 of the sky is covered in cloud, then that is going to be the cloud cover. We'll see a quarter of the circle is colored in, right? Then we have the wind direction. Now, the wind direction, I'm going to draw one coming from, let's say, from this side here. Imagine that this is an arrow going into your circle, right? I'm not going to draw in the arrow, but can you imagine that's an arrow going into the circle? So the wind is coming from the side. That is north, just write it up here, north, south, west, and east. So this wind is coming from the southwest, so this will be a southwesterly wind. Then the little feathers on the arrow, they give us the speed of the wind. A long feather would count 10 knots, and a shorter one would count 5 knots. So in this case, I have 10, yes, I'm correct, 10, 20, 5 knots, the wind speed. So I've got the southwesterly wind, because remember, winds are named after the direction from which they come, and this wind is coming from the southwest. So it's a southwesterly wind blowing at a speed or velocity of 25 knots. Right. we then also have 2 temperature indicators. So the one temperature, let's just make it 28, and the other one, I'm going to make it 7. The top number will be the actual air temperature at the time the measurement was taken. So when this information was gathered and the thermometer was checked, the temperature was 28 degrees Celsius. We don't write the degrees Celsius symbol on our weather station model because we're trying to save space on our map. So just the 28, but learners, candidates, when you are giving the answer, let's just say you are asked in a question, what was the air temperature at this particular place where this weather information was given, then you need to write your answer as 28 degrees Celsius. If you only write the 28, if you do not write the degrees Celsius, even though that part is correct, it will be marked wrong. You need to write the full 28 degrees Celsius for this to be marked correctly. So be very, very careful. On the weather station model, we don't write the degrees Celsius, but when we give the answer, when we're explaining what is happening here, then we have to write down the degrees Celsius. And usually, not always, but usually, on whichever side this arrow is, the weather information is usually on the other side, just to balance things out. But that's not always the case. It depends on the map and how much space is available. Then over here, we will have a symbol. We will have a symbol for the type of precipitation. And that symbol over there represents drizzle. And the lower number represents the dew point temperature. Now, you would have learned in grade 10 last year that dew point temperature is the temperature at which condensation is going to occur. In other words, if the air temperature drops to 7 degrees Celsius, then the water vapor in the air will condense to form little droplets of water. Clouds will form and it will probably rain. So the dew point temperature is the temperature at which condensation will occur in this air mass at this particular place. Now, I want you to think for a minute. You can determine the likelihood of rainfall by looking at these 2 numbers. I'm just going to write another set. Of numbers down. Let's say on a different one, the air temperature is, say, 15 degrees Celsius, and the dew point temperature is maybe 12 degrees Celsius. Now, in situation A, we wrote it in blue, and in situation B, we wrote it in orange. Which one of the two places is rain more likely to form? The answer is in place number B. Why? Because here the temperature has to drop by, what is 28 minus 7? 21 degrees. The temperature has to drop from 28 degrees to 7 degrees Celsius in order for rainfall to occur. That's a drop of 21 degrees. But over here, the temperature has to drop from 15 degrees Celsius to 12, which is a 3 degrees Celsius difference. So learners, a simple way to check whether or the likelihood of rainfall occurring is to just subtract the dew point temperature from the air temperature. The bigger the difference, the less the likelihood of rain. The smaller the difference, the greater the likelihood of rain. Because it's easy for temperature in a matter of a few hours to drop from 15 to 12. But it is less likely, not impossible, but less likely for it to drop from 28 degrees to 7 degrees Celsius. And in a nutshell, that is our weather station model. Let's recap quickly. We have here cloud cover, 1/4, right? This is 1/4, or we can call it 2/8, okay? Or we could call it 25%, okay? Of the sky is covered with clouds. So the cloud cover is 1/4. The air temperature, the temperature of the air is 28 degrees Celsius. The type of rainfall that is prevalent at the moment is drizzle. Remember, if there's no precipitation taking place, then this will just be left blank. This area will just be left blank. So if there's nothing there, and you are giving the weather at this particular place, you can write down air temperature 28 degrees Celsius, dew point temperature 7 degrees Celsius, cloud cover 1/4, and then you can write down type of precipitation, none, because nothing is recorded there. But in this case, that is the symbol for drizzle. There is wind blowing. It is coming from the southwest. It's a southwesterly wind, and it is blowing at a speed of 25 knots. So, in a nutshell, this is what you would have been taught in the class since grade 10 already. Now let's go back to our presentation, just to go and have a look at what we see in front of us on the screen and see what we can identify. So, there's a weather station model. Let's start right at the bottom with the cloud cover. You will notice that the cloud cover is overcast. Okay? The cloud cover is overcast. Do you see that? And how do I see it's overcast? Because when I look over here, I see that my circle is completely colored in, which means that it is overcast. That would be 3/4, that would be a half, that would be a quarter, that would be 1/8. So it is completely overcast. The entire sky is covered with clouds. The air temperature is 27 degrees Celsius. Notice I write it out full, 27 degrees Celsius. The dew point temperature is 24 degrees Celsius, written out in full with the degrees Celsius symbol. The precipitation symbol here signifies rainfall. Here we see the different types of precipitation: drizzle, rain, snow, shower, my favorite, thunderstorms, fog, and hail. We notice the wind direction here. It's coming from the northwest. So it's a northwesterly wind, and there's a long feather and a shorter one, so that would be 10 plus 5, giving me 15 knots. And these are the weather conditions portrayed by this particular weather station. Okay, let's go further. And here are two weather station models. Now, what I want you to do, I'm literally going to give you a minute, 30 seconds each. Just write down on a sheet of paper in your books, just write down the information for each of those two weather stations. The first one has been done. Let's have a look at the first one. Do you agree that the air temperature is 18 degrees Celsius? Yes, we can see the air temperature over there, 18 degrees Celsius. The dew point temperature is 12 degrees Celsius. We can see that. The cloud cover is half of the circle has been colored in. The wind is coming from the northwest. There are 2 long feathers, so it will be 20 knots. And the weather station symbol signifies fog. Right, so I'm giving you a minute to quickly write in the information for this weather station and then the information for that weather station, and then we'll check if you did it correctly or not. So just take a minute. We will leave this on the screen, and I'm giving you a minute. Right, that was a very fast minute, but let's see. So, you should have gotten, oops, wrong slide. Let's just do it, let me do it with you. So for this one, the air temperature, by the air temperature you will write 35 degrees Celsius. By the dew point, you're obviously going to write 10 degrees Celsius. The cloud cover, we can see the entire circle is colored in, so it is overcast, or 8/8, overcast. The wind direction is coming directly from the east, so it's an easterly wind blowing. The wind direction is east. The wind speed 25 knots, 10, 10, 5, 25 knots. And the weather conditions over here is thunderstorm. That's the symbol for a thunderstorm. Let's have a look at this one. The air temperature is 22 degrees Celsius. The dew point temperature is 9 degrees Celsius. Cloud cover, 0. Clear skies, no clouds. The wind direction is coming from the northeast, and it is blowing at a speed of 25 knots. And the type of weather, there's no precipitation, no rainfall at all occurring at this particular weather station. And remember, always write down your units. Your temperature is in degrees Celsius, your wind speed is in knots. None of the other elements have units. It's only degrees Celsius for air temperature and dew point temperature, and then knots by the wind speed. Those are the only units that we use with our weather station models. Right. Now, I want you to draw the following weather stations. So the first one was drawn for us. The cloud cover to be overcast, so there it is. The wind direction had to be northwest, so it's coming from the northwest. The wind speed had to be 25 knots, so there it was drawn in. Air temperature of 16 degrees Celsius. Dew point temperature of 12 degrees Celsius. And the weather symbol, the weather symbol had to be showers. Okay? So, you now have to draw the following. I'm going to go back for you 2 slides quickly, just so that you can have a look. You got that? Maybe take a picture of it with your cell phone, or if you're on your PC, just do a screenshot or something of that. Then this will help you. Okay? Right. So, you've got to draw the 2 weather stations. And once again, I'm going to give you sort of 30 seconds each, and then you can have a look at what I've drawn. I'm going to draw it so long. I'm not going to show you while I'm drawing it. I'm just going to draw it quickly while you're busy constructing yours. Okay, I'm done with my first one. I'm going to draw my second one now. And then we'll have a look at whether our sketches match. Right, let's have a look at what I've drawn. So for the first one, our cloud cover had to be 1/4. Does everybody agree with me? That's correct. Wind coming from the southeast. Wind speed of 5 knots. Now notice I left my error deliberately. I initially drew that there and then I scratched it out. And the reason was, in the southern hemisphere, we always draw, so if this is my wind, that is where it is. If that's my wind, that is where it is. If the wind is there, you notice something. It is always to the left of the wind symbol. Am I doing it right? Oops, sorry. I'm teaching you the wrong work, sorry. It's the other way around. That was the northern hemisphere one. So in the southern hemisphere, always to the left here. So there, from that side, if the wind is coming from there, the weather station will be there. If the wind is coming from there, the weather station will be there. So you can see, as it is going into the circle, it is always on the right-hand side. If you're standing at the circle, it's on your left-hand side. So when I draw that, my wind is coming from that direction, and it is on the right-hand side. There's my 5 knots, there's my 22 degrees Celsius, my 16 degrees Celsius, and my symbol for fog. Okay? Then, on the second one, here we go, 3/4 cloud cover, wind coming from the northeast. It is 15 knots, a long one and a short one, 15 knots, 28 degrees Celsius, 16 degrees Celsius, and thunderstorm activity. So I think you can all identify now the elements of a weather station, and you can also all draw your own weather station model now. You should be more comfortable with it. Practice it a little bit, play around with it. Go and look at Synoptic Weather Maps and find 5 weather stations and write down the weather conditions at each of those weather stations. Your teachers from this point onwards, going into grade 12, will teach you now that you can identify the different elements of the weather. We can use these elements to tell us a little bit more about what is happening in an area or what is going to be happening. You will learn to start identifying patterns. When this is the case and that is also happening at the same time, this will be the result. Those sorts of things are what we will be looking at from now going into grade 12. Right, so let's move on. Let's look at the weather station model before and after a cold front. Now in front of you, you see a map of South Africa and you see a cold front, which is an element of a mid-latitude cyclone. Now, you will be doing mid-latitude cyclones in detail in grade 12, but you've started looking at fronts in grade 10 already, and you've continued looking at them. And what do you know at this stage about a cold front? You know that when a cold front passes over a place, and for us who live in the Western Cape, who live in Cape Town, we've just come through our winter months now, and we've experienced many cold fronts. And we know that many things happen, but the three main things that happen when a cold front passes is, firstly, let's have a look at our slide. The first thing that happens is that the temperature will drop. Secondly, the cloud cover will increase. And thirdly, precipitation will occur. So in other words, temperature will drop. It's going to become cold. The cloud cover will increase. There's going to be more clouds visible in the sky, and precipitation means that some sort of rainfall is going to take place when a cold front passes over. So when I look at a weather station model ahead of the cold front, remember the cold fronts move from west to east as you're looking at it from your left to your right on the screen in front of you. So initially the wind direction will be from the northwest. Notice in that red weather station model, this is showing me the weather ahead of the cold front. The wind direction will be northwest, and it will be around about 15 knots. That 15 knots is not a constant. It can be a little bit more, it can be a little bit less. But cloud cover will be approximately half, 50%, and your temperatures will be relatively high, like 22, and there will be a big difference between your air temperature and your dew point temperature, which means it will be less likely to rain. But behind the cold front, notice the wind direction changes. We say that the wind backs. You don't have to explain it in grade 11. Next in grade 12, you will understand the meaning of the word back. But the wind direction backs. It changes from northwest to southwest. Notice the drop in atmospheric pressure the drop in atmospheric temperature that has taken place. The temperature has dropped from 22 degrees Celsius to 14 degrees Celsius. It has become much colder. The dew point temperature, however, has increased. Now, learners, remember, this does not mean that it has become colder. All that this means is that now, in order for rainfall to occur, for precipitation to occur, the temperature needs to drop over here. It needs to drop to 11 degrees Celsius. Before, the temperature had to drop to 5 degrees Celsius in order for rainfall to occur, for precipitation to occur, and rain to fall. Now it only has to drop to 11, and notice only by 3 degrees Celsius. And that is why over here there's no type of precipitation, because of that big difference between the two. But here, because your air temperature is so close to your dew point temperature, there is the symbol for rainfall. Rainfall is already starting to occur, and as I said, my wind direction has changed. It is now coming from the southwest, and the wind speed is much higher. Here the wind was blowing at a speed of 15 knots, and here, when the cold front has passed, remember this cold front is moving from west to east. The cold front is moving in that direction. So all the places this side of the cold front will experience these conditions, and as the cold front passes over a particular place, these conditions will be replaced by these ones. This air must be behind the cold front, where the temperature is colder or lower, where the dew point temperature is a bit higher, where it's going to rain because these two are so close to each other, where it is overcast, where the wind is now blowing from the southwest instead of the northwest, and where the wind speed has increased. So one of the things, teach yourself, find synoptic weather maps where there are cold fronts on it, and have a look at the station models, the weather station models ahead of the cold front and those behind the cold front, and see if you can identify the differences. Now, our next topic that we're going to look at is the characteristics of synoptic weather maps. In other words, what are these elements? We're going to jump right into it. What are the elements that are characteristic, things that we constantly see on a weather map? And the first thing that you're going to notice on any synoptic weather map are the pressure cells. High pressure cells, they usually but not always have a H in the center, and low pressure cells with an L in the center. So here I can see a low pressure cell that has an L in the center. There's another one with an L in the center. There's a high pressure indicated by an H. There's another high pressure indicated by an H. But this low pressure cell here does not have the L. I know that it is a tropical cyclone because I know that this is the symbol for a tropical cyclone. And next year you will know this too. This tropical cyclone has a name. It is called Eileen. Tropical cyclone Eileen. And just a little secret, so that next year you'll know it already when your teacher teaches it to you. When you look at tropical cyclones, if you look at the name, that letter indicates to me how many tropical cyclones have already occurred in this area. Because it starts with an E, it is the fifth letter of the alphabet, A, B, C, D, E, 1, 2, 3, 4, 5. So this is the fifth tropical cyclone that has occurred in this area for the year. Isn't that cool? Okay, so you can tell by looking at the name of the tropical cyclone how many have occurred. So high pressure and low pressure cells are two of the characteristics of synoptic weather maps. We can identify them by either the L or the H. We can also identify low pressure cells by other symbols, like in this case there's a tropical cyclone symbol, and this cold front here is part, if we were able to follow this cold front all the way further down here, we will see there's a low pressure cell there also, because this is part of a mid-latitude cyclone, which is also a particular type of low pressure cell. Right, we have isobars. So isobars are lines that join places with equal atmospheric pressure, and these lines develop certain patterns which tell us a little bit more. So for example, on this isobar, all the places along this isobar has an atmospheric pressure of 1008 hectopascals. This one here has 1012. That one there has 1016. So we can see the isobaric interval, the interval between one isobar and the next one is 4 hectopascals. So we will see isobars on synoptic weather maps. They are further characteristics. In addition to high and low pressure cell, isobars are also characteristics of synoptic weather maps. There is a tropical cyclone, and as I said, it is Eileen, starting with an E, making it the 5th one for the season. Now, grade 11's another little secret, just our secret, don't tell anyone else. If they don't do geography, don't tell them that your tropical cyclones occur in summer. So when you see a tropical cyclone on the map, we're going to come to that now, you will know that this is during the summer season. The absence of a tropical cyclone doesn't mean that it's winter, because it can still be summer without a tropical cyclone. But definitely when you do see one, then you know it is definitely summer. I spoke about the isobaric or isobar interval. That's the pressure difference between two consecutive isobars. We said in this case it is 4. This high pressure cell that I referred to earlier has a specific name. It is the South Indian high pressure cell. Look at where it is, but you need to remember that for next year. Then, also characteristic of a South African synoptic weather map is the weather conditions at any weather station. In this case, we are looking at Port Elizabeth, so in other words, any weather station. And we can see at Gqeberha, Port Elizabeth or Gqeberha as we know it, is the air temperature is 25 degrees Celsius, the dew point temperature is 18 degrees Celsius, the cloud cover is a half, wind direction is coming from the southwest and blowing at a speed of 25 knots. And in this case, Gqeberha was chosen, but we could have asked you to give the weather conditions at any of the weather stations. Then cold fronts, I explained to you earlier that cold fronts move from west to east. You don't have to know for grade 11 much about mid-latitude cyclones, but just remember that a cold front is not an isolated feature. It is part of this mid-latitude cyclone that we'll be studying in detail next year. And then there's the South Atlantic high pressure cell. So on the South African synoptic weather map, there are 3 high pressure cells that you need to be able to identify, and it's quite simple because look at where the South Atlantic is situated. It's in the South Atlantic Ocean, right? You can see where South Africa is. Here's the South African coastline. There it is. You with me? And there, this is the Atlantic Ocean, and it's in the south of the Atlantic Ocean. And this high pressure cell is in the south of the Indian Ocean. So it's my South Indian high pressure cell. There's a coastal low. You'll learn a little bit more about that also. It's a low pressure cell found along the coast. I won't go into more detail than that now. Now, the third high pressure cell is one known as the Kalahari, and it is usually found just here. And the reason that we don't see it now is because this is a summer map. Remember I said tropical cyclones indicate summer? And this high pressure cell is only present during the winter months. So if you see a H here, smack bang in the middle of South Africa, then you know that this is the Kalahari, the third of this set of triplets, South Atlantic, Kalahari, and South Indian, except the Kalahari isn't here, because the Kalahari only comes out to play in the winter months. In the summer months, the Kalahari high pressure cell is replaced by this low pressure cell called a heat, as in H-E-A-T, a heat low or a thermal low pressure cell. Right, now we're going to differentiate between synoptic weather maps representing winter season and synoptic weather maps representing the summer season. Let's have a look. What are the differences? Oh, that looks like a lot, doesn't it? But it's not that hard. So there's 2 synoptic weather maps. The one is actually indicated as being summer, and the one is indicated as being winter. Now I know it might seem a bit small, you might not see everything on the map, but it will become clear because after this we will look at individual ones. So, for summer, the first thing you could be asked, first of all, you could be given a synoptic weather map without these indicators on. And you could be asked, does this map represent summer or winter conditions? Grade 11 is the first thing. Go look at the date, if the date is printed there. Because we know, this map, for example, the date here is the 17th of February. Now, anything between November and February, even up to March, could be considered to be summer. We know that. So the date will be a clear indication of whether it is summer or winter. If it's a winter map, I can see the date here is the 15th of, I can't even see if that's an 8 or a 6. It looks like an 8 to me, 2009. Okay, so if the months are between May and August in the date, then that's usually a good indication that it's a winter map. Look at the air temperatures at the individual weather stations. Look at the air temperatures. We don't have any weather stations on these two particular maps, but on a summer map, the temperature will be high. Most of the temperatures will be above 20. And on the winter map, the temperature will be relatively low. Most of them will be below 20 degrees Celsius. Remember, there could be 1 or 2 places in winter where the temperature is higher than 20, but for the majority of the places on the map, the temperature is going to be lower than 20. And similarly, there could be 1 or 2 places over South Africa where the temperature is lower than 20, in summer even, but that would be the exception, not the norm. Most of the places will have temperatures above 20. During summer, the cloud cover over the interior is high. Why? Because of that heat low that I spoke about earlier, that thermal low. This indicates that this low pressure cell tells me that there's a huge amount of air rising, strong upward convection currents. And we know that when air rises, cloud cover will form. And with the excuse me, with the Kalahari high pressure cell being present here during winter, that indicates to me that it's cold, and this cold is busy sinking and pressing down hard on the surface of the earth. And when air sinks, we will have very little cloud cover over the interior, but we do have lots of cloud cover over the coastline, especially the southwestern Cape, because of the cold fronts. Okay, so here the interior will have a lot of cloud cover in summer, and the Western Cape should have clear skies. The weather stations here should show clear skies, whereas in the winter months, these weather stations will show you lots of cloud cover, and the weather stations over the interior will show very little cloud cover. During the summer months, your rainfall, if you look at the weather stations, here will be lots of rainfall over the interior, over the east coast, mainly in the form of thunderstorms. Okay, and here on this map, most of the rainfall will be limited to the south, to the Cape Town area, the southwestern Cape, and then along this coastline here, as my cold fronts move across, bringing rainfall there. Okay, the type of cyclone that you will be prevalent in summer, we mentioned it already, tropical cyclones. There is the example of a tropical cyclone that will be prevalent. And here the mid-latitude cyclones. Here's an entire mid-latitude cyclone. In fact, there's a family of mid-latitude cyclones, 1, 2, 3 following one another. This one would be the oldest because they're moving from there across. So this one there would be the oldest, that would be the second oldest, and this is the baby in the family here. This is the third one. This one still has to reach Cape Town. Okay, and the cold fronts here pass south of the country. Notice where the cold fronts are. These cold fronts are not going to touch Cape Town. They're going to move past the south and then move across there. Whereas these ones here, we can see, are clearly moving across the southern African land mass. And that's the basic difference between summer and winter conditions. So let's look at the winter synoptic weather map in detail. I can look at the date. The date that was written there is the 29th of the 6th month, 2020, and I know that June is winter in South Africa. Okay, so the date is my first indicator that this is a winter synoptic weather map. Then I look at the air temperature. There's one weather station, the air temperature is 13 degrees Celsius, but if you look at closely at all the weather stations on this map, you will see most of the weather stations are recording temperatures of lower than 20 degrees Celsius. I also see a mid-latitude cyclone prevalent. I don't see any tropical cyclone, so that's a further indicator that it's possibly winter. I can also see the cold front is passing over the land mass of South Africa. So here's the coastline. Watch here, the coastline goes to there and around. So this cold front is passing over the southern African landmass, over the country. If it were summer, it would be passing south of the country. It wouldn't make contact with the country at all. There's a high pressure over the interior. Remember, we said that this is the Kalahari high pressure, which is only present in winter. Cloud cover, where here over Cape Town, Western Cape, overcast and cloud cover, and look at the weather stations further inland. All clear skies, okay, which is an indication of winter, because no rainfall and no clouds form here during the winter months because of this high pressure, this air busy sinking over South Africa. Cloudless interior, we just mentioned. If we come to the summer synoptic weather map, once again the date, this one is the 22nd of February, right? It's definitely summer. Notice the air temperature over Uppington is 32 degrees Celsius. All the other weather stations that I can see from here, 27, 26, I see a 28, I see a 30. They're all higher than 20, so it's definitely summer. I can see a tropical cyclone Eileen, once again that same one we looked at earlier, being the 5th tropical cyclone for the year, and tropical cyclones only occur in summer. Now remember what I said, learners, if there's no tropical cyclone, it doesn't mean it's winter. The presence of a tropical cyclone is a clear indicator that it is summer, but it can also be summer without. It can also be summer without a tropical cyclone being present. So a tropical cyclone, yes, it's summer. No tropical cyclone, it can still be summer or it can be winter. We need to go and look at other indicators. Okay, let's go back to our synoptic weather map. There we have a cold front which is going to pass south of the country. It's not going to touch. It is just scraping by the south of the country, but it is not going to touch the landmass, so it's not going to bring rainfall. The cloud cover over the interior is now overcast. Look at all those weather stations over the interior. And then if you look at the weather station at Cape Town, you will see clear skies. There's a low pressure over the interior. You see that there? Okay. That's called the heat or thermal low. Right. And that's the difference between summer and winter conditions on a synoptic weather map. We are now going to look at application to grade 11 climatology. What do I mean by that? You've been taught various content in your climate section in term 1. In term 1, your teacher taught you all the content that you needed to know for grade 11. So what I'm going to attempt to do now, I'm going to attempt to take that content that you were taught and show you how that content can be shown on a synoptic weather map, how you can be tested on that content on a synoptic weather map, and how you can identify all the features and the elements that you were taught in term 1 on a synoptic weather map. So let's go and have a look. So these were the main topics that you covered. You started looking at high pressure and low pressure cells. It's one of the first things you did at the beginning of the year, way back in January already. If you can remember that far back, I hope you can. You then looked at the concept of pressure gradient, the difference in pressure between two places, and how pressure gradient causes a force known as pressure gradient force, and that causes air to move from a high to a low pressure, and the movement of air we call wind. We also studied the various pressure belts. We studied the various pressure belts of the world. We looked at different major wind belts, especially the westerly winds and the easterly winds. There were more than that. There were 3, but these were the 2 main ones that we looked at. And then we also looked at the role of the oceans in controlling climate. And I'm now going to look at how we can identify all these topics on a synoptic weather map, how we can be tested on all 5 of these topics on a synoptic weather map. Right. Let's start with high and low pressure cells. Very simple. You must be able to identify a high pressure cell and know that in the southern hemisphere, look at the drawing of that cell. That air is busy. That air of that high pressure cell is busy sinking. It is moving down. Look at the blue arrows, circularly moving downwards in an anti-clockwise direction. Okay. Then the value of the isobars increase towards the center. So when you look at any high pressure cell, look at the isobars and you will notice that the value of the isobars increase. So when I'm looking there at the South Indian high pressure cell, in that little blue rectangle with a blue dotted line, you will see the atmospheric pressure goes from 1008 hectopascals to 1012 to 1016. The atmospheric pressure increases towards the center, and that's how I can identify a high pressure cell. With a low pressure cell, your air is rising and the circulation of air within the cell. Notice the terminology I'm using, the circulation of air. I'm not speaking about movement. Movement of air is in a straight line. That is northwesterly winds, southeasterly winds. When we speak about the movement of air within a low pressure or high pressure cell, we speak about circulation. And you can clearly see on those two diagrams there, the air in blue on the HP, on the high pressure cell, sinking in an anti-clockwise manner, and then the orange arrows on the LP, we find the air rising in a clockwise direction. Right. And the value of the isobars here, they decrease towards the center. And if we look at that tropical cyclone Helene, we will see the isobars drop from 1004 hectopascals to 1000 to 996. The value of the isobars are decreasing towards the center. That's how we can differentiate between a high and a low pressure cell, even if there's no H or L indicated in the center of that cell. Right. Pressure gradient. Pressure gradient is the difference in pressure between 2 points. Now, when the isobars are close together, as in the case that you see in front of you, you will notice those isobars are close together. Now, I want you to look at that weather station that has been circled in red. This one over here. This weather station that has been circled in red. Here we can see the isobars being close to one another, and that causes a steep pressure gradient. Okay? Notice here to 1012, 1016, 1020. Notice the air is moving in this direction, but I want you to see the wind speed there. To me, that looks like 30 knots. Yes, it is, 30 knots. Okay? Strong wind. Where the isobars are close together, the wind is going to be strong. Right. Where the isobars are further apart, notice here, there's an isobar, there's an isobar, there's the next one, compared to this here where they are relatively close to one another. These isobars are spread far apart. So we say the pressure gradient is gentle or it is weak. And any wind in this vicinity here is not going to be strong. Look at all these winds here. They're all 5 knots or less. They're all 5 knots. That symbol there means less than 5 knots there. Okay, 5 knots, 5 knots, 5 knots. So the wind speed is gentle, and the reason for that is my isobars are further apart, giving a very, very weak pressure gradient. Right. Pressure belts. Here is a little video, which I was hoping was going to work. Just give me a second. Okay, let's skip that. So, let's move on. We have a global air circulation pattern. So, you know this already. As complicated as this diagram looks, you know this diagram already. Starting in the center at the equatorial low pressure, which in this case coincides with the ITCZ, you know that at the equator, in the vicinity of the equator, we have the equatorial low pressure cell or low pressure belt. We also know that these pressure belts move north and south during the seasons, but we'll come to that now. Then we have on either side of that, we have the subtropical, let me just put my laser pointer back on, we have the subtropical high pressure cell here between 30 and 40 degrees in the northern hemisphere, and then also between 30 and 40 degrees in the southern hemisphere. And then we once again have the subpolar low pressure belt and the subpolar low pressure belt, and then we have our polar high pressure and our polar high pressure. So you need to know the location of these pressure belts. You also need to know that the westerly winds blow from the subtropical high pressure to the subpolar low pressure in both hemispheres. The tropical easterlies blow from the subtropical high pressure towards the equator in both hemispheres. Okay, those are the two main. There's also your polar easterly winds, but we're not going to be looking at that now. You also know that winds deflect to the right in the northern hemisphere as an effect of Coriolis force, and to the left in the southern hemisphere. And you know the conditions, and these two are the important ones here. The equatorial low pressure, very, very hot. Air is rising, ascending, the pressure is low. Very, very cold at the polar regions, so you have a low pressure. Okay, here we've got air from the equator sinking. At the poles, very cold descending air. Sorry, this was the subpolar here, and this is the polar regions. Your teachers will be getting this PowerPoint presentation, so ask them to see. I'll send it to them as a PDF as well, and this is very a nice and useful diagram for you to use when studying this particular topic. But let's look at it on a synoptic weather map. So what do we see here? Over here, I see the subpolar low pressure and the polar high pressure, because this cold front separates the polar high pressure. This air here would have come from the polar high pressure, and that air there is my subpolar low pressure, and this is the front that separates those two air masses. I can identify my subtropical high pressure. That area there falls within the subtropical high pressure belt. We can see the winds that are blowing. Westerly winds. Look at the direction of all these winds here. These winds here form part of that westerly wind belt. That is why my mid-latitude cyclones move from west to east, because the westerly winds are pushing them in that direction. See that? I can see my easterly winds. Notice these winds here are all blowing more or less in that direction. These form part of the tropical easterly wind belt. Right, now we're going to look at the role of the oceans. You know this, you did this in grade 10 already. So we see along the east coast of South Africa, we've got higher temperatures because of the warm Mozambique, and then along the west coast we've got lower temperatures. So grade 11s, we've now come to the end of our presentation for today. Now remember, all that we did today was just revise what you've been doing already through the course of the year, especially in term 1. It is up to you now to go and study this work. But I think you have a better understanding of how the various topics that you've studied for the year tie in with Synoptic Weather Maps. Thank you for staying so late, and good luck for your exam, and I hope to see every one of you in grade 12 next. And thank you to the teachers who remain behind after school as well. We appreciate you. God bless. Have a good day. Thank you.